I was going to start the second video on sample problem 2, but I was just looking at the end of sample problem 1, and there's a few things I want to mention that you can maybe add into your notes. My answer, 3185.15, that was slightly different than what the book got, and the reason is this here. If you look back at the K constant, I'm using 9 times 10 to the 9. I noticed that the textbook uses 8.99 times 10 to the 9. So virtually the same value, but a very slightly different version. This always ticked me off in university. Different textbooks, different courses, different professors. A lot of the constants that you use in science are slightly different, or they have another decimal place or whatever, depending on who or what book you're using or who you're talking to. Don't worry about it. As long as you're doing things right, you're going to get final answers that are virtually the same. And this is what I wanted to mention, if you round them to proper scientific notation and significant digits, which is what they're going to get you to do more of next year, you will get the same answers. So if I round that to one significant digit, I get 3.2 times 10 to the power of 3, the same as the book. This is very important as well, and I forgot to have that on there. You need direction. This question specifically asks to calculate the net electric field. Actually, they don't specifically say direction, but the idea is you do have to have directions on your answers. So this is to the right because the original diagram showed it. That's going to be more of an issue with sample problem number 2 because we're going to have vectors pointing in different directions at the end of this question. But let's not get ahead of myself here. Let's go one step at a time so that you understand. All right, so in this question, right away, actually, they don't have an unknown point shown on this diagram. They mention it in the question. They say calculate the magnitude of the electric field at the origin. So even though they haven't shown it on here, the idea is they want you to do this. They want the net electric field right here. So again, there is nothing there. There isn't charge number 3. This isn't a Coulomb's force question or a... we're not calculating the force between these two charges. We're calculating the net electric field at this empty spot in space over here. So start by, don't even look at any of the numbers in the question. Don't look at any calculations. Just look at how the signs work. And if they don't show charges or the signs on the charges in the diagram, put them in yourself right away before you begin. Q1 is listed as, oh, they didn't put a sign here. They just left it blank. That means it's positive, unfortunately. They do this all the time. Sometimes they don't type a positive sign, but they do always type a negative sign. So you can see charge number 1 is positive. I'm going to write in a positive sign. And charge number 2 is negative. I'm going to put in a negative sign. And before even beginning the question, just think about how this works. So charge number 1 is going to create an electric field around it at all positions, no matter how far away you go. They want you to look at a distance that far away. It's a positive charge, so it will create an electric field, and we have to put some kind of a direction on the electric field. Positive charges have field lines drawn away from them, and you don't have to draw these arrows in here. I'm just saying, no matter how far away you go, I'm going to draw an arrow away from it. So electric field, that's a terrible arrow. Electric field number 1 is going to be away from that charge. Similarly, let's look at charge number 2. It will create a field around it at all positions, including way out here at this position they want us to look at. And it is a negative charge, which tends to have field lines drawn toward it from all positions. Toward it, toward it, toward it, toward it, toward it, and even over here at this point, toward it. So that is electric field 2. So you can see where this question is going. It's virtually like any other question in this course we've done, just with a different formula. You're going to have 2 vector answers in the end, and you need to put them together to get one final net force answer. So let's calculate them separately because you don't need to do this all in one shot. That's why drawing a diagram and having the directions on the lines is very, very helpful. So let's figure out electric field 1. K, Q1, divided by the distance from the charge to that point, which this time I'm going to write it as r squared, just because the textbook actually uses r, and I want to stress that the distance is a distance. It's also a radius of a circle. And we'll sub in the values here. So K is 9 times 10 to the 9 Newton meter squared per Coulomb squared. This charge, it's a positive charge, but don't put the sign in here. You've already used signs, making a direction sort of map of what the question looks like. So I'm only going to write in 4 times 10 to the negative 6 coulombs. And the distance on the bottom, I'm going to put brackets and square it right away because I don't want to forget. 3 centimeters is given in the question. So convert that properly, and grade 12s do it wrong all the time. There's 2 decimal places you have to shift over. 0.03 meters squared. Okay, so take out a calculator, enter those simple numbers, and watch that you don't put a negative 9 on the K value. You will do that eventually. Everybody does. You're so used to writing negative 11 on universal gravitation constant that you'll eventually put negative 9 in your calculator without thinking. But hopefully not. This time you get an even answer. There are no decimals whatsoever, of 40 million. Boy, that's a lot bigger than the answers in the previous question. Newtons per Coulomb. But it is what it is. Charge 2. What is the electric field 3 centimeters away from charge number 2? So charge 2 and a distance away squared. Same thing. The answer will be in the same ballpark, just because these values don't change too dramatically. Charge number 2 is negative, but don't use the negative sign. It's 2 times 10 to the negative 6 coulombs. And the distance, just by the symmetry of the diagram, is the same, 0.03 meters squared. So sub that into a calculator, and you get 20 million newtons per Coulomb. Okay, so those are your 2 electric field answers. And you don't add them together or subtract them in this case because of what the diagram looks like. These are vectors that are in completely different axes. So the only way that you can get a true net value for these is you have to arrange the vectors tip to tail. Take one of these vectors and shift it over. I'm going to move this one down, and I'll redraw it like this. I'm going to leave electric field 1 alone, and electric field number 2 I'm going to extend from the end of it tip to tail. And so the answer to this question, the final answer to this question, will be this. It will be side C of a right angle triangle, using those 2 electric fields as your side A and your side B. So simple Pythagorean theorem, C squared equals A squared plus B squared. And this is going to be a pain to write it all in here, but I am going to take 40 million newtons per Coulomb, square that, and add 20 million newtons per Coulomb, and square that, and get a final answer in the end. So let's see, 40 million squared plus 20 million squared, and a root of that answer in the end. That comes out to 44,721,359.6 newtons per kilogram. And then the textbook is going to round this to proper scientific notation, whatever that might be. In this question, proper scientific notation would be 2 decimal places. So they should have rounded this to 4.5 times 10 to the power of 7 newtons per kilogram. Or sorry, newtons per Coulomb. Now, after that, you would need this. You would need to do the direction. You would need to say what the direction is. You would need to do a sine, cos, or tan calculation inside this triangle. But we can cut this question short, and the reason we can cut it short is because of this right here. They specifically say in this question, calculate the magnitude of the electric field. So they didn't want you to continue on and do the direction as well. But had they wanted you to do that, you would just do a tan calculation for opposite over adjacent, take the inverse tan and get a final answer, and you would have to express it as down some number of degrees to the right. So that concludes these two examples. There are 3 homework questions to try out today. The first question is actually just ridiculously easy. It's only 1 charge and 1 distance away from it. So it's really only questions 2 and 3 that involve some thinking. Question 2 is very, very much like sample problem number 1, but there's a slight difference. The way the diagram's drawn and the way the distances are labeled, so be careful. Question 3, the diagram isn't drawn yet. There's only a word description. So make sure you draw a diagram first. Make sure you include the signs on the charges and think about the directions on the electric fields that you're going to get, and then put them together in the end. I see there's no final answer on this question. My apology. I'm going to leave it that way because I can't put it on there now. Work out your best possible answer for number 3, and we'll go through the full solution on tomorrow's post, and you can see if you did the question entirely right, and if not, you can see what your mistake was.